Well, let's move to lesson 3, which is titration and titration analysis. So a titration is used to determine the concentration of sample. So the concentration of a sample. And the sample is placed on the flask with a volume that we know, with a known volume. So we know the volume, and we are figuring out what is the concentration of the sample that we have. Okay, and then this sample is placed in the flask. The burette is filled with titrant. And has a concentration that we know what it is. A solution of a highly certain concentration is called standardized solution, and we did the standard solution. Okay, we did a dry lab for standard solution. And a sample is a chemical that is a sample is a chemical that can be obtained with high purity, okay, of a certain and mass that can be measured at certain. Okay, so let me bring you a picture of a titration equipment and setup. So this picture is a picture of the way that the titration lab is set up. So what we have here is a ring stand that it's just to help hold the burette. Okay, and then the clamps are holding, those are the clamps and are holding the burette. The burette has a standardized solution and the flask has the sample solution. So now what we will do is we will be able to measure using opening here, we will be able to measure the volume of the standardized solution that we are using, and then we will be seeing what is the concentration of the sample that we are using. So now here on the sample, what we are adding is also the indicator, and the indicator based on what reaction or what are we titrating. The indicators are different and will be used for the specific situation that we have in place. We will stop adding the standardized solution into the sample solution when the indicator is having a light pink color. Now, the standard solution, in other words, is known as the titrant, and sample is the sample. Okay, so as a result, if we have like a very precise equipment that we are measuring, what we will see is a pH curve, or the anatomy of titration pH curve is something like this. So we'll see that the pH, as the volume is increased up to a point where the equilibrium is reached, and then after that we will see an increase of the pH as well when the volume is increased. So this is the And what it is actually is when we have a base and an acid reacting together, or like they are reacting together. And then what we see here at this point is the pH is 0, and this is what we are looking for. This is the equivalence point. But on this case, what like a picture like this, an anatomy like this, a curve like this, a pH curve like this, is telling us that we have one inflection point. Or one inflection point, because the curve changes only once, which means that if the acid or the base are with one hydrogen or one hydroxide. Titration curves are used to determine when titration curves are used to determine when a sample is completely neutralized. So when you see this curve here, completely neutralized means pH is equal to 7. And this is represented by the equivalence point, which for simplicity is known as AQP. To find the equivalence point is the middle of the inflection point, inflection curve. So where the curve changes the direction from curve up to curve down, okay, is the inflection point. Right where the curve changes the direction from curving up to curving down. Okay. Strong acid. For the strong acid, the pH is between 0 and 3, and strong bases, the pH is between 10 and 14. Now, what do we have here is when we see here the volume of base is actually the volume in flask, which is equal to the volume of titrant and the volume of the sample. Okay, and then the pH here will be the pH in the flask. Okay, so this is the pH in the flask. And keep in mind what we are doing in the flask. We are adding flask. We are adding titrant and sample. Okay, so keep this in mind when we are dealing with strong acid. You have to expect that the pH is 0 to 3, or when we are dealing with strong base, the pH is between 10 and 14. Now, how do we know that we are dealing with strong acid? Is in your data booklet, whatever is above hydronium. Okay, so now when we see that the equivalent point is 7, exactly 7, then what we are dealing is, or the anatomy of the pH curve will be something like this. So this is the volume of titrant. And when we have a strong acid and a strong base that they are reacting together, it goes like this. So this is strong acid and strong base. Okay, and then the pH is 7. pH is 7. And when we have a weak acid and a weak base that they are reacting together, then what we will have is something like this. weak acid and weak base. And again, the pH is 7. So a weak acid is titrated with a weak base, or a strong acid is titrated with a strong base. Let's talk about indicators in a bit. Okay, now when we have equivalent point that is greater than 7, what will happen is the anatomy of the pH curve in titration will be something like this. Here we have volume of titrant, and here we have the pH value. And if 7 is somewhere in here, okay, then the equivalent point greater than 7 will be somewhere above 7. Okay, and then what it is happening is that we have a weak acid and a strong base reacting together. So a weak acid and a strong base. So the equivalent point is somewhere in here. Okay, greater than 7. The pH is greater than 7. So when a weak acid is titrated with a strong base, the pH is greater than 7. And on the case when we have the equivalent point less than 7, the anatomy of the pH curve will look something like this. Volume of titrant is a strong acid, with a weak base. So if 7 is somewhere in here, then the equivalent point will happen here. So strong acid and weak base. The pH is less than 7. So when a weak base is titrated with a strong acid, the pH is less than 7. Okay, so now if we talk about indicators, the good indicator in this case will be bromothol in blue. A good indicator for weak acid and weak base, sorry, weak acid and strong base will be also in yellow. And for weak base and strong acid will be orange 4. And as I said even before, that the indicators that are in the flask are dependent on the situation that we are at. Okay, so let's take a look at this example here. Here we have a curve, a pH curve, but it's starting at about 3 pH. And let's label everything, label the pH and the volume of the titrant on the curve. So the pH will be here. And the volume of the titrant will be here. So what do we see is that the volume of titrant. And what is the pH of the sample? The pH of the sample is starting here, so it is 3, pretty much 3. You can say that is on the middle. So the pH of the sample is 3. What is the pH of titrant? So the pH of titrant is, let's make it with a different color. The pH of titrant is this point here, the end point. And we can say that is about 13, 12, 12, 12.5, 12.7, something like this. The equivalent point is, let's make this, the equivalent point is this point here. Okay, and the pH of the equivalent point is about 8.5. So it's the red dot. The pH of the equivalent point is about 8.5. What will be a good indicator to show the end point? Phenolphthalein will be a good one. And we choose this based on the information that we have for the indicators in the data booklet. Okay. So titration data collection. When we are collecting data from titration, we will add titrant into the flask with the sample and indicator. Okay, and indicator until it reaches the equivalent point. Okay, until we reach the equivalent point, which means that the color, the indicator color is very visible. It's visible, but not too strong. Okay. Don't forget that the goal of the titration is to determine the concentration of the sample. Okay. So now, when we have, if we have a situation like this, that we have a titration of 25.0 milliliters of sodium hydroxide with 0.325 molarity of hydrochloric acid, you end up with a table like this. Now, the sample is sodium hydroxide, and the titrant is the hydrochloric acid. Why is the hydrochloric acid? Because when you see this, the concentration of hydrochloric acid is known. So this will make it as the titrant. Okay. Now, the information that you get is something like this. For the first trial, you start with 0.6 and then goes to 16.5, and then the color of the indicator is changing. And then you go to second trial, starting at 16.4.5 and going down to 31.8. And then the third trial, so and so. Okay, so the very first step is, let's write a balanced chemical reaction. So what do we have with the information that is given? What do we have is sodium hydroxide is reacting with hydrochloric acid to produce, we know what it is produced, sodium chloride and water. Those are balanced. Now, what do we have here is that we have 25.0 milliliters of sodium hydroxide with a concentration that we don't know. We will figure it out. And we have the concentration of hydrochloric acid at 0.325 molarity. Okay, we don't know the volume of the titrant, but based on the information that we have here on the table, we will find the volume. Okay, so after we write this as the balanced chemical reaction, what we will do is we will figure out what is the volume. So the volume added in milliliters will be the difference between final volume and initial volume for each trial. So what we have here is 15.9 is the first one. 15.3 is the second one. So what I'm doing here is 31.8 minus 16.5. The third one is 15.3, sorry, 15.2, not 3. Yeah. And 15.2 milliliters. Okay, so what do we do here as the first step is we find the volume by subtracting the final and initial. Subtracting initial from final. From final volume. So known as final minus initial. Okay, and the second step is that, as you see here, we have 3 trials. Okay, so sorry, 4 trials. So we have 4 trials. So now what we will do is we will eliminate any trial that are not within plus minus 0.2 of each other. Okay, so we will eliminate the trials that are not under plus minus of 0.2 of each other. When we take a look at the information that we have the first trial is 15.9. The second trial is 15.3. The third trial is 15.2 and 15.2. So naturally, we will eliminate the 15.9, okay, trial 1. So we will eliminate 15.9 milliliters and keep trials number 2, 3, and 4. Depend on the situation, because they are, in this case, if they are not in an experiment, if they are not within plus minus 0.2 difference, then you have to do more trials to end up into 3 trials that have a difference of plus minus 2 volume added on it. And then as the third step, what we will do is we will find the average of the volumes that we keep. So the average is the sum of all, and in our case will be divided by the number of trials, which are 3 in our case. So in our particular case, we'll have 15.3 plus 15.2 plus 15.2, the whole thing divided by 3. And the unit will be milliliters. So the average volume added which is the volume of hydrochloric acid, will be 15.23 milliliters or 0.01523 liters. So this will be the other piece that we need in our information to figure out the concentration of the sample. And now, with this information added into our reaction, then we can work things out. So now what we have is 15.23 milliliters. So the concentration is given, the volume is found by the table, and then now what we do is we do stoic. We are looking for the concentration of sodium hydroxide. So we'll start with what is given, 0.01523 liters of hydrochloric acid times molarity. So 1 liter of hydrochloric acid is 0.325 moles of hydrochloric acid. We found the moles of known. We will use the molar ratio to find the moles of the unknown. So 1 mole of hydrochloric acid, 1 mole of sodium hydroxide. So liters and liters are cancelled out, moles and moles are cancelled out. And now we will use the amount, the liters that we have for sodium hydroxide, which we know the volume of the sample as 25 milliliters or 0.025 liters of sodium hydroxide into 1, and then we are ending up with moles per liter, which is the concentration, and we will have 0.198 molarity of sodium hydroxide. So this is what you do at titration. So if we wrap it up again, we have set up the titration, and then based on the trials, so we figure out the volume that is added. If it is needed, we eliminate a volume that is more than plus minus 0.2 milliliters, and then we find the average, completing that other piece of the hydrochloric acid, that in this case is a hydrochloric acid that is the volume, and then we do stoic after that and find the concentration. So even on this case here, use the information to determine the titration of the concentration of sulfuric acid. So what do we have with lithium concentrate to determine the concentration of sulfuric acid? So we have to add more information here. So now what do we have here is titration of 12 milliliters of sulfuric acid with 0.75 molarity of lithium hydroxide. Okay, so we have those as the volume added here. Now let's start with the reaction. H2SO4 aqua solution plus 2 lithium hydroxide will give us 2 water, liquid, and lithium. Okay. Now, what is given here is that the volume of sulfuric acid is 0.012 milliliters, and a molarity, so concentration is question mark, and then molarity of lithium hydroxide is 0.75. And we have to find the volume using the table. Okay, now let's work with it. Volume added and will be in milliliters. For the first one, 17.9 minus 0.3 will be 17.6, 17.5, 17.7, and 18. This will be eliminated because it is more than 0 plus minus 0.2 in difference with the other. So the volumes that we will use will be those ones here. Let's find the average volume. Will be 17.6 plus 17.5 plus 17.7. The whole thing divided by 3. As long as you have 3, then you are good. And this will be 17.6 milliliters or 0.016 liters. And now that we have that piece of information, so 0.01676 liters, not milliliters, liters. Now that we have it, let's do stoic. Okay, so we'll start with what is given. So we'll have 0.0176 liters of lithium hydroxide using the concentration. So 1 liter of lithium hydroxide, 0.75 moles of lithium hydroxide. So liters of hydroxide and liters of hydroxide are cancelled. Now that we know the moles of known, we will move to the moles of the unknown. So we'll have 2 moles of lithium hydroxide is 1 mole of sulfuric acid. So moles are cancelled out. And this is in 0.0120 liters of sulfuric acid. So then the units will be in moles per liters of sulfuric acid. And as calculations, you will go 0.0176 times 0.75, divide the whole thing by 2 times 0.0120. And the number will be 0.55 moles per liters or molarity of sulfuric acid. I hope that this makes sense. Let's see another example, and then hopefully this will be even better. So use the following table of concentration, and there is no information here, but I will add it now. 0.25, 9.81, 9.81, and 19.48, 19.48, 28.83, 28.83 is 38.38. So the difference on volume will be 9.56, 9.57, and 9.35 and 9.55. So this one will be eliminated because it is more than plus minus 0.2 difference, or in within. And then the average volume will be 9.56 plus 9. Is this right? 1 second. I will double check. Actually, this is 9.67. And we are eliminating this because this is the lowest one. And we usually, when we do this, it's like, even though that this is not. So 9.67 plus 9.55, they are all correct ones. So yeah, the values are within 0.2 milliliters. This is the one that we will eliminate, and the volume will be 9.59 milliliters. Now that we have the volume, let's write reaction. So what we have is titration of 45 milliliters of magnesium hydroxide with 1.25 molarity of HNO3. Okay, so the chemical reaction will be, or a balanced chemical reaction will be HNO3 plus magnesium hydroxide will produce magnesium nitrate plus water, and be 2 molecules of water. Now what is given here? So based on the information that we have here, titration of 45. So volume of magnesium hydroxide is 45 milliliters or 0.045 liters. And the concentration is unknown. And what we have here from the given is that molarity is 1.25, and volume from the table is 9.59 milliliters or 0.0959 liters. And now what we do is start. Starting with what is given, so 0.0959 liters of HNO3 using the molarity 1 liter of HNO3 and 1.25 moles of HNO3. So liters and liters are cancelled out. We know now the moles of known. We will move 2 moles of the unknown. And in order to do so, we will use the molar ratio. So 2 moles of HNO3 is using up 1 mole of magnesium hydroxide. 2. So moles and moles are cancelled out, and this is diluted into, or is into, 0.045 liters of magnesium hydroxide. And now in terms of numbers, what do we have is 0.0959 times 1.25 times 1 divided by the whole thing by 2 times 0.045. And the molarity is 0.133 molarity of magnesium hydroxide. Now you can move to assignment and figure out all the questions. We will deal with questions that you may have in class. This ends up lesson 3.